Welcome back, everybody. We are doing primary clarification part 2. In this episode, we're going to be doing a project, and then we're going to do some exam prep on the whiteboard later on. And that project that we're going to be doing, though, is draining that clarifier, cleaning it out, relining the effluent launder, and doing an inspection. In order to do that, I still need a primary clarifier because I have a trickling filter. So what I'm going to do is they've engineered this plant where I can shut some valves, open some other ones, and this half of my secondary will turn into a primary clarifier. Okay, and what's really cool about this is I'm going to be able to actually later in the video open these grates up, and you'll see the difference between secondary trickling filter effluent and primary clarifier effluent, really, because it'll be going over the weirs. I just want to talk real quick about this in channel. It looks a little icky. These leaves are just, if I tried to get every single leaf ever out of here, it would be a full-time job. So I just kind of manage it. And then there's some floaties in there. That's not the worst thing ever. It's just a little bit of secondary sludge. We have skimmers in here that take that stuff off, but inevitably there's going to be some floaties that make it past. And then we actually pull the water. The water flows from the center of this pool. So that stuff's not going to chemical induction. I skim it off with a pool net and throw it into a sludge pit, and it heads to a different process. Pretty easy little task. Okay, so now this in channel looks quite a bit different, doesn't it? So this is now my primary clarifier effluent. It is going to secondary processes at this point. Been running like this for a few days. And I really like to show this juxtaposition here between the primary and secondary. Like, look at the difference in water quality. And all it's done is gone over that trickling filter. Okay, the biofiltration has done its job. And if you want to learn more about trickling filters, check out the links below. I'm going to put the primary clarifier video part 1 at the end of this. It'll pop up on your screen, but look in the links for trickling filters. And there's always going to be this like sludge here that kind of floats over, and I get that with a pool net, or I hose it down and it goes to the secondary processes. But this is the weir overflow. So this is these weirs right here. The linear length of weirs is how we calculate our weir overflow rate. And on the whiteboard, later in this video, we're going to talk about what your typical weir overflow rate should be. And yeah, look at the difference in water. So this is my secondary now, okay? Secondary clarifier, effluent, and primary. Let's get into that drained primary clarifier, and let's take a look at some of the mechanisms and how that effluent launder looks and why it looks the way it does. Okay, here we are with a drained clarifier, and I've got the mechanism running so you can kind of see how slowly those rakes move. And what their purpose is the reason they're angled that way is to push the sludge towards the center. This is actually a sloped floor going towards the center, and that's what's called the hopper. And there's a piping situation in there where it pumps. We're able to pump to our digester. We don't have thickening here, but sometimes you'll be sending it to a sludge thickener or maybe sludge conditioning. It depends on the design of your plant. And on the note of sludge thickening, if this were a gravity thickener, these rakes would also have pipes that would be going up, a few feet, and that helps with the gasification. When sludge is sitting in, you have a high sludge blanket for a long amount of time, gas forms and it can float your blanket, and that's not what you want. And sorry, you got all my gear all over the place, but I'm gonna point out over here is our skimmer arm for the scum, and it's moving over really slowly. It's attached to this whole apparatus. And right here, the reason I'm filming over here and not where I have a better catwalk is I wanted to show you the failed liner, and this is really our target. What happens here, and I mentioned this in part 1 of primary clarification, is that when hydrogen sulfide and air mix, it creates sulfuric acid, and that we lose our liner, and then that sulfuric acid gets its way, it'll start eating the concrete. Okay, that is an exam question. It's really something else. We're gonna inspect this thing and see if we can figure out if there's any scraping along the floor or any of that kind of mess. And then, yeah, we're also gonna get this liner cleaned out, the effluent launder rather, cleaned out and sandblasted and relined. Let's take a look. All right, here we are a few days later. It was really good to get some better lighting installed in here. That was not actually part of the project, but it became part of the project, and I'm so happy we did it. I got used to how dark it was in here. It was light enough for me to operate, but not really great for working on a construction project like this, and it is so much better now. So I'm glad that we went ahead and did that. Now you can see they went ahead and scraped that failed liner up mechanically, and the concrete's in really good shape. Thankfully, we're doing this at the right time. Sandblasting crew comes in tomorrow, and they're going to clean up the rest of that liner, and then they'll get in here. It'll be about a 3-day coating job. So we're about a week to a week and a half out from putting this clarifier back online. Now I want to point something out. You see that those holes there, there's one, they're all around. If you go back to Clarifier part 1, I'll link to it at the end of this video, you can hear me talk about how I don't use weir overflow rate in this clarifier because I don't have weirs to overflow. I use surface loading rate. That's how my supernatant gets into the launder and moves to the next process, okay? So I use surface loading rate and I use a detention time math formula, okay? So the next thing we're gonna do is go ahead and start the sandblasting and coating process, and I will pick up the video after either we are sandblasted or after we are coated. It depends on my access to this room. Okay, so they have finished their first layer of sandblasting and they've exposed the aggregate. Now what they're gonna do is they're gonna mortar this launder, and what you can see, they've given me the profiles here. The one right there is kind of where we're at right now, pretty rough. Then they're gonna mortar to give the one my thumb's on, and then they're gonna come and sandblast to put that profile on, kind of like texturing drywall, kind of same concept. And what it'll do is it'll let the epoxy liner actually grab. So they're gonna, after they're done doing that, they're gonna prime it and line it. Now look at what just we discovered. Oh my goodness. So during the sandblasting, they weren't sandblasting that, but there's pretty aggressive atmosphere in here, and it peeled that paint up off of that drum and it exposed a really gnarly rusty spot. So that actually is where the water is introduced. You'll see as we start filling up the clarifier kind of how it comes in. But I need to get that specced out. I bet you there's a creative way we can actually repair this or replace it, maybe line it with poly. I don't know. I'm gonna talk to some vendors and see if there's a way we can do that repair without, you know, replacing this whole apparatus or cutting into any of the welds. It won't be very long before we're back here making that repair. Okay, so the launder is lined and patched up for all the holidays that they had, and we're ready to put this in service. There's some, still, you see railings down there. There's still some work to do with putting the, everything back together, and some more cleanup work down here before we put it in service. But I want to go down there and do a little show and tell with you. And just for liability reasons, just so you know, I am doing a confined space entry. This is not a video about confined spaces. I do have an attendant. They don't want to be in the video, and that's fine with me. So you won't see the attendant, but just know that I am being safe. So anyway, let's go down there and take a look at some of the infrastructure. Okay, so we've already talked about the rakes and how they work earlier in the video, but this is kind of an up close and personal view. These are stainless steel blades. They float about 6 inches, or it's not 6 inches, half an inch off the floor. We actually have some scraping in some areas, and we're gonna lift that up. As you can see, a lot of the coating is coming off the angle iron here. This isn't something we anticipated. That, along with the drum, like I mentioned earlier in the video, need to be recoated, but the change order was so expensive we have to go for board approval. Clarifier's already, this project's already been delayed, not delayed, but taking way longer than we thought. And the good news is the carbon steel on this thing is in good shape. The contractor scraped it real good and said, oh, you know, it's mostly superficial rust. We can get by putting it back in the water. And the good news is it'll be submerged. So when things are submerged constantly, you don't have to worry about as much issues as we do in that launder where it got all eaten up. It's really the air mixing with the hydrogen sulfide that's the killer. We went ahead and make the command decision. We need this clarifier back on by the 4th, so we're just gonna scrape all this paint off of this angle iron in the drum, and we're just gonna put it back into service and come back. We're gonna award a contract to somebody and get back here in the next few months and get this stuff recoated. So let's talk about this drum for a second and its purpose. Okay, so we've talked about the rakes, we've talked about the hopper where the sludge goes. Now let's talk about this drum. It's called a baffle, and you'll see that's the influent line that comes in and it dumps water into it. The water line when this clarifier is full is typically about right where my fingers are, so it never overflows the drum. That means the water has to go only a certain direction. The only way it can go is down, okay? So we're forcing water to kind of do this motion. You'll actually look in those manuals. If you look at the diagram in the WEF or the SAC State manual, you'll see this, almost this whole picture written out. You'll see the arrow of where the water flows kind of like this, right? So what it does is if we were just to put that water in here without a baffle, it would just skim across the surface and go wherever it wanted. So we're making it go a certain direction. And you see all these tubes here, that's for pulling up the supernate, and we talked about that earlier. So anyway, the whole goal here is to turn over the clarifier several times a day, enough frequency where you don't go septic in the clarifier, but slow enough, so fast enough that we don't go septic, but slow enough that as the water does that move, the heavier solids fall, okay? And the floatables float, all right? So we've already talked about how the sludge, solids fall, sludge is collected, boom. We also have our skimmer arm up here, and you can see another pipe apparatus over there. That is the scum beach, And so, or however you want a scum collector mechanism, but we call it the scum beach. And that pipe right there actually is where the scum is deposited, and it flows into another pit where we pump it to the digester. So anyway, there's a little bit more cleanup to do. Next thing we're going to be doing is they're going to level these rakes out. I'm not going to film that. We're just going to get this thing going. We're up against the clock. So the next thing you'll see is me putting this back into service after all of this is said and done, and then we'll go to the whiteboard for a lesson. Let's go. Welcome everybody to the whiteboard segment of this video. Thank you for sticking around to this segment. And if you've gotten anything out of this video so far, please like the video, subscribe to the channel, and pass these videos to your friends and colleagues, and let's help folks get certified. The other real quick housekeeping item I'll do is I'm going to go over some weir overflow rate, surface loading rate, some tidbits here. Any math problem on here is going to be in the links below. I've done separate videos about them already, so you can go check them out. When I get to CEPT, I did a coagulation and flocculation video where I go into greater detail about what we're going to talk about. So that'll be in the links below as well. And I'm going to make a comment about transporting thickened sludge to digestion. Anaerobic digester full episode like today's was, like this one was. A lot of fun. We made a repair, and I got into some real helpful anaerobic digestion discussion in that on a whiteboard segment like this. So that'll be in the links below as well. Okay, housekeeping over. Let's talk about all these different items here. And just so you know, this is more of an advanced and intermediate conversation. Beginners, you don't need to know this for the grade 1, but I do encourage you to stay. The clarification part 1, which will pop up on your screen like I've already said in this video, will go into the more basic stuff you should know, but please stick around. This is good stuff. So the weir overflow rates typically are 10,000 to 20,000 gallons per day per foot. Lineal foot, not square foot, not cubic foot, lineal foot. I have read WEF material that says for larger plants it's going to be 30,000 gallons per day per foot, but I wanted to note that for the WEF people that are watching. But this is your textbook number, 10 to 20,000 gallons per day per foot. And before I go any further, how this is going to be opposed to you, why you need to know it. You may be straight up asked on a multiple choice question, but when you get to advanced testing, they don't just straight up ask you stuff. It's not a do you know, it's a do you know and know how to fix situation. So what they would do is give you a math problem, you would work it out and say your weir overflow rate was outside of this window. You were either lower or higher. You would need to tell them what you were going to do. Are you going to do you have a spare clarifier to put online if your overflow rate's too much? Do you have, can you take one offline if it's too little? Is there flow equalization strategies you can use? Should you reduce recirculation? From, like in my plant, I've got a recycle stream coming from my secondary sedimentation. Is that a situation I could address? Stuff like that. Okay, so that's how you should be prepared to answer these questions. Surface loading rate, also known as surface overflow rate. I've also seen surface settling rate. So they're all synonymous. If you're just pumping influent into the primary clarifier, your average is 800 to 1,200 gallons per day per square foot, and your peak flow should be 3,000 gallons per day per square foot. That's pretty textbook. If it's influent plus WAS, it is going to be 600 to 800 gallons per day per square foot, or 1,500 to 2,000. I've read 2,000 a lot of places, but then I saw 1,500 some other places. Just 2,000 gallons per day per square foot is a pretty pretty safe target. Now let's talk about this WAS thing. I don't do this. I waste to a separate digester, but I want to discuss why WAS might be sent to the primary. And if you're unfamiliar with what WAS is, WAS stands for waste activated sludge. So this is the sludge in an activated sludge system that you are wasting out so you can balance your food and microorganism ratio or whatever process control measurements you're using. Since I don't do this, I did a little research and I wanted to explore this with you. And if you do this in your plant, please put in comments below and tell people why you guys do WAS to the primary. The first and most, the one that makes a lot of sense to me is you're reducing the load on the secondary with seed. So you're seeding the primary with active microorganisms, okay? And that'll lower the BOD load on the secondary processes because they're going to get to work. Now, there's no oxygen for them to get to work, but they're there and ready to get cooking when they're aerated. And typically, WAS has a little bit of DO left in it, so they might be able to get to work. But at the very least, you're seeding. I can see a reality where nutrient removal, this can help nutrient removal, but I'm not going to dive into that right now. If you use it for nutrient removal, please put it in the comments below. Now, what makes total sense to me, because I do this with my secondary sludge from my trickling filter, which is quite a bit more liquidy and not as active as I would say activated sludge is. It's the only location in the plant for transport to digestion. So if you have a digester that takes a mix of secondary and primary sludge, the engineers may have said, hey, it makes a lot of sense just to send the WAS to the primary clarifier. There it can settle and it can thicken because like in my plant, I run about an 8,000 MLSS. So that's a 0.8% total solids. That's still a bit thin to send to an anaerobic digester. My WAS goes to an aerobic digester, so I can get away with a lot more there with the thickening. But if I'm going to anaerobic digestion, I need the thickest possible sludge. So I can see where they would go to a primary and let it settle with the other sludge, and maybe you can get it out of there at 2% solids, you know? So, so yeah, only place in the plant for transport to digestion and also thickening. And it's a lighter sludge than primary typically is, and so there's your lower flow rates. It's a fluffy flock that, unless it's really old and oxidized, and it'll drop like a rock. We'll get into that when we get to activated sludge. I don't want to confuse anybody, but I did want to talk about it because somebody might ask, well, why the heck would I do WAS to my primary? Those are the two reasons. And again, if you know a third or fourth or fifth, please put it in the comments. Detention time. Your target detention time in a primary clarifier is 1 to 3 hours with an average target of about 2 hours. Any less, you will probably not get good settling and it's hard on downstream processes. Any more, you could get septic. And that's really hard on downstream processes. You don't want septic conditions. Okay, CEPT stands for Chemically Enhanced Primary Treatment. The two most common, and by the way, for all those who are into rare earth flocculants, I'm not going there. I'm going in a place where we're talking about exam preparation and what is normally what you're going to find in a plant. And we can get into nuanced stuff at a later time. Ferric chloride and aluminum sulfate, alum, it's written alum, you'll see ferric and alum written. They are the most common coagulants you would use, and you would typically, I didn't write it up here, typically followed up by an anionic polymer. I get into that in that coagulation flocculation whiteboard. Check it out, links below. Your BOD reduction is going to be higher, and you're going to be more like 40 to 60% BOD reduction and more of a 60 to 70% TSS reduction. Quite a bit more than your standard primary clarifier just using gravity. Okay, and I have those other values in that part 1, so go check out part 1. H2S removal. I only put this in here because of my emphasis on it during our project in the earlier part of this video. You will either see ferrous chloride, calcium nitrate, or hydrogen peroxide used for H2S removal. Okay, this is getting more into a odor control lesson or even collections, but it can be administered at the influent point of entry. And what's the next step after the influent is primary clarification. So ferrous chloride cannot be used in CEPT unless oxidized to ferric upstream. I'm not going to get into that, but know that, okay? Ferrous chloride is what you use for H2S removal and odor control. Ferric chloride is what you use for chemically enhanced primary treatment and a slew of other things in the treatment plant. Ferric chloride's got a lot of uses. Calcium nitrate has a trade name Bioxide. I'm going to give credit where it's due. I got that one out of the Wahlberg study manual. I don't use calcium nitrate, nor have I ever, but it's a really cool way to get rid of hydrogen sulfide. Read up on that. Bioxide is a trade name that you probably need to know about. And hydrogen peroxide, 50% strength typically, is also used for hydrogen sulfide removal. All right, everybody, thank you for joining me on this video. I had a lot of fun with this project. It took a ton more time than we thought it would, but in the end, it was totally worth it. I hope you got something out of this, and until next time, have a great day.